So I thought it'd be a good idea to do an example problem which covers the various concepts that we talked about in the last learning module. Here we're given a diagram which shows three forces that are actually acting on this O-shaped connector. They're forces that are exerted by cables which are connected. Those cables are tending to pull the connector. F3 pulls partially to the right and partially up, and we have F1 and F2 that you can see as well. And we were told the magnitude of each of these forces. And we're asked to resolve each of them into their x and y components. Another way to say that is to write each in rectangular form. So just getting you familiar with the kind of multiple terminologies that we'll be using throughout the course. And by definition, to write a force in rectangular form is to write the vector as its x component, scaling the I hat unit vector, which is the unit vector along the x-axis, and the y component, scaling the j hat unit vector, which is the unit vector along the y-axis. So let's go through and do this. So we don't need to worry about it now, but when we have forces associated with tension in a cable, where a cable is actually acting upon a connector like this, the line of action of the force is collinear with the cable itself, and we have the magnitude specified. So let's decompose F1 first. Well, let's just look at F1. What do we notice? Well, the book is actually drawn in a coordinate system. We have an X and Y coordinate system. And note that F1 is perfectly aligned along the Y-axis. And we can kind of envision little j hat sitting along the Y-axis. So all that we need to do to express F1 in rectangular form is use the magnitude that we were given and scale j hat. So F1 is just going to be, and I can write 0 I hat if I want, but it's 320 J, and this is all measured in units of newtons. And it may be beneficial to show the x and y components separately, because when we ultimately determine the resultant, we will add the components, all of the x components together and all of the y components together. So let's do F2. If you notice F2, I'm going to kind of redraw the vector, and we were told that its magnitude was 420 newtons. And we know that with respect to what the book is drawn as a coordinate origin, they're calling this the x-axis. They're calling this a y-axis. And that is a very convenient choice of coordinate systems. But the angle which is labeled 45 degrees, key point that I want to emphasize is this is not that theta that's defined in all of the formulas that we showed in the slides. Namely, if you say, oh, I can get the x component by just taking that magnitude and multiplying by the cosine of 45, you would be incorrect there. So an easier way to do this problem is just to take, and I'm going to kind of redraw this again, and draw a force triangle where you represent each of the side lengths by vectors which are parallel to the x and y component. And what I mean by that is, yeah, this is the x component. Sorry, I should say this is the y component. Sorry, long day already. This is the x component. This interior angle is 45 degrees, but I'm not going to overly worry about the signs at first. I will manually adjust the signs, and what I mean by that is the plus and minuses that go on each of the components as needed. I'll do it manually. I won't just focus on using the formulas directly. So when I look at the y component, how would I relate that if it represents this side length of the triangle to the information I know, which is the length of the hypotenuse along with this interior angle? Well, notice relative to the angle that I know, the y component is opposite. So I could say that the sine of 45, and again, the reason that I chose to use sine is relating back to so, ka, toa. For the angle that I knew, the 45-degree angle, the side length in question was opposite, and I know the hypotenuse. So I chose to use the sine function. Sine of 45 is the ratio of the opposite side length, which corresponds to the magnitude of the y component, divided by the hypotenuse, where the side length here is modeling the magnitude of the force. So I can compute the y component by taking 420 and multiplying by the sine of 45 degrees. And I will leave that there for now. We'll make the computation eventually. You might remember sine of 45 as root 2 over 2, or about 0.707. But let's actually focus on this x component, because this is very important. So if I say that cos of 45, again, going back to SOHCAHTOA, is the adjacent side length fx divided by the hypotenuse, which again, that side length corresponds to the magnitude of the force, 420, I could write that Fx equals 420 cos 45, but I have to be careful here. And again, when your work is graded automatically, it only matters what your final answer is. But we want to be careful in our notation here, and I'm going to add in a negative to account for the fact that usually the way these force vectors are written, it's the magnitude times positive I hat. And I know, looking at this, that the x component is in the negative I hat direction. So I'm manually putting in that negative to account for the fact that this goes along negative I hat. If you don't want to manually adjust this, you would have to not use the angle that you were given, but the conventional direction angle referenced from the positive x-axis with counterclockwise rotation. So if you don't believe me, just put in 420 cos 135 into your calculator. And the way I got 135 is, of course, those two angles would add to 180. So we'll make the calculation. That's hard to read. Sorry, cos. Yeah, it's good enough. When we get to the point of forming the resultant vector. So let's do F3. So that was an important example because what I'm trying to emphasize is oftentimes you're given angles that don't plug into the formulas directly, and you kind of have to do some manual adjustment. So for F3, we'll notice that, again, we can resolve it into an x and y component, and I'll call that F3x, and I'll call this F3y. And I should have been more careful kind of keeping notation, but I kind of avoided having to be careful in my bookkeeping because I'm doing each force one at a time. So this is magnitude F3. And you might say, well, hey, those formulas that I need involve the cosine of theta and sine of theta, and that's clearly the angle that I would be interested in knowing, but I'm not given it in this case. But what I'm told is that force triangle is, its geometry is described by a similar 3, 4, 5 triangle. So what we know from this, we could determine theta by taking an inverse tangent of 4/3 or something like that. But remember, we really don't need theta. We need the cosine of theta, and we need the sine of theta. So from this triangle, I can determine in this particular scenario for this theta that cos theta is adjacent divided by hypotenuse, or 3/5, and sine theta is opposite divided by hypotenuse, or 4/5. So therefore, in this problem, and I will kind of draw a line to keep our work separated, F3 x component is going to be the magnitude of the force, which we were given as 580, times the cosine of theta, which will just be 580 times 3/5, and F3y is going to be 580 times the sine of theta, which is just going to be 4/5. And then I can write the entire vector F3 is whatever that number comes out to be for the x component, scaling I hat, plus whatever number that comes out to be times the y component, that is the y component rather, scaling j hat. And we can kind of do a sanity check, right? We know that these are going to be positive numbers, and we can look at F3 and tell that it has a positive x, a positive y component. We can look at Fy and tell that it only has a y component, no x component. In F2, assuming we remember that the sine and cosine of 45 degrees is positive, we see that the x component here is negative and the y component is positive. So let's actually go. I'm going to use a software program called Matlab just because I don't have a calculator here with me. Matlab is a program that many of you will be using as you kind of move on in your engineering career. So I'm going to clear my workspace. Just ignore everything else other than what's going on in this white area right here. So one thing that I wanted to mention, when you use a calculator, so I'm going to start by computing the x component of F2. Remember that when you ask it to take the cosine of something, you have to make sure that it knows you're talking about an angle in degrees. If you're using a traditional calculator, that will be done by setting the mode. But if you're using a software package like Matlab or Python, you will do that by actually appending a little d to the end of the function. So that's what cos d means here. And not surprisingly, that if I do that, and I'm going to actually show this intermediate result, even though in general we don't want to present, we don't want to round any results until we get to the end. I'll show it now for the first part of the problem, which just asks me to decompose the vector into x and y components. And then when we go back to the resultants, we'll kind of see if there's any difference that we get from intermediate rounding. So F2 would have an x component rounded to 3 sig figs of 297. And then for the y component, I need to take 420 times the sine of 45. And to 3 sig figs, I would get 297 as well. And I computed that, kind of a little bit flustered here. I got a lot going on today. But obviously, when you get the same answer, you might say, oh, what the heck is going on? At least the same in terms of absolute value. But remember, a 45-degree angle, the definition of a 45-degree angle is for every step right, take a step up. So the sine and cosine are the same. In a similar fashion, let's do F3. So I will say that if I take 580 times 3/5, I get the x component of F3, and that is 348 I have. And if I compute the y component of F3, it was not 3/5 of the magnitude, but 4/5 of the magnitude, which will be 464 J hat. So that is F1. That is F3 rather. I'll rewrite F1 here as well. And just to show you, if you were just to do this problem in the book as requested, these would be your final answers. And I will show you back on the .cam. And do a sanity check always. Look at them and make sure that they reflect the actual drawing. F1 should be positive y, no x component, positive x, positive y, negative x, positive y. And we do kind of have those answers reflected in our results. So I'm actually going to stop the video now, and I will do a new video where I actually compute the resultant vector and actually express it in polar form.